Start recording. All right. So, I forgot to put up what the lecture is. Oh, it's all right. Um, how you guys doing?
Finals week are coming in, so not so great.
Yeah, everything's coming to a head as everything is due, and all of your knowledge and work over the last semester gets tested next week. Yay! Um, I love finals week. Got so much less to do. Um, and this final's on Monday, which is great. So it's out of the way like right away. Also, you don't have all that much time to study for it, but that's all right. You did the homeworks already, so you shouldn't have to do a whole ton of studying because you're already well versed in all the things, right? That's not actually how it works, but so okay. Today we're going to talk about dark matter. There's a homework due tomorrow. Office hours tomorrow at 4 o'clock. Holler if you want different office hours than that. Trying to think if there's anything other business related things to say right now before we get into the details. I can't think of anything. So we'll go over. So Thursday we'll go through the homework, and I'll go over study material. That's going to be mostly, hey, go through the homeworks and make sure you know how to do all those things. And then once you've done that, go through the lecture slides and make sure that all the stuff on the lecture slides is familiar. And once you've done that, go rewatch all of the videos and look for trends of patterns of things that I say. And if you have time to rewatch all the videos, I commend you, because I don't think there's actually enough hours. Because there's like what? There's 26 of them, so that's 26 75-minute lectures. So anyway, mostly go make sure you understand the homeworks, because that's where I put all the things that I care about you doing. So okay, today we're going to talk about dark matter. So we're going to talk about why dark matter, which has been a running theme kind of through the whole semester. But we'll glue some of those ideas down. Then we'll talk about what the dark matter candidates are, and then we'll talk about how we're going about looking for them. So there's 3 different ways that you can make dark matter, or 3 different ways we can find dark matter particles. We'll talk about those searches. So it could be a bunch of things. So this slide is super important. Make sure that you have a good understanding of everything that's here and what they mean and what kinds of questions I might ask you about these things. How does each one of these things tell you that there is dark matter? So rotation currents of galaxies, X-ray temperatures and clusters, dispersions of galaxies, galaxy velocities and clusters, and dispersion of stars in elliptical galaxies. So those ways tell us that there's dark matter by way of comparison with the luminous matter. So those tell us that there's missing stuff, but doesn't rule out it's just stars that have all died, or huge planets made out of rock that we just can't see for whatever reason. Those aren't ruled out by these. However, the other ones do. So large-scale structure, which I didn't say a ton about, but essentially the power spectrum of the mass, you don't get the right answer if you don't include pressureless dark matter. So if you run a simulation, and this I was realizing this earlier as I was going through these slides. I'm like, I know how I need to do that again in the future. What I really should show is one of these papers where they did a simulation with dark matter and a simulation without dark matter, and you get a much steeper spectrum. Stuff clumps a lot harder without the dark matter. So the large-scale structure of the galaxies in the universe, nucleosynthesis in the early Big Bang. So the relative abundances of deuterium, hydrogen, and helium all tell us about the density in the early universe. The acoustic peaks of the CMB tell us about the dark matter, because the acoustic peaks tell us how dense things can get. The dark matter makes things dense, the pressure makes things less dense. So pressure versus dark matter are in the peaks of the CMB. And we talked about baryon acoustic oscillations, and I'll show one of those. I'll show that plot again. So feel free to Oh, actually, I got an idea. I'm gonna make another assignment. Let's see, work rate. Sorry, squirrel brain takes over sometimes, and um, I want you to ask questions before the review on Thursday. So I'm gonna make an assignment that's worth 0 points. That is just a spot for you to stick questions as you're doing your stuff. And I had this thought earlier, and I think I'm going to actually follow through with it now while I'm thinking about it. Although the internet is terrible, this should be a real quick thing. God damn it. Everything's a headache. This would be so quick. I'll live. Okay. Sorry. Finish locking in. Okay, I'm going to stop that. Make a list of questions for Thursday. And if you email them to me, in principle, this thing will finish futzing around. The Duo loaded, but the other thing didn't. There you go. Okay. I'm going to put it in the readings. Okay, now there's a spot. It doesn't have a due date because it doesn't have any points either. So that's just a spot for you to stick questions. Yeah.
I was just wondering. You said these rule out baryonic dark matter. Is
Yeah.
that what that's saying?
Yeah, these all rule out baryonic dark matter. These all say that there is dark matter. There's a bunch of stuff. It's not protons. It doesn't have pressure. Most of these are because whatever is massive also doesn't have pressure. Oh, there's another one. There's only one of them, but the bullet cluster is a really good one. That's a really good indicator that there's dark matter, but not that there's dark matter and it's not protons. It doesn't have pressure. So, what is this stuff? Okay, in all of known existence, there are 4 forces, and that's it. That's all the forces of all the things that could possibly happen. There's only 4 things that can happen. There's gravity, there's the electromagnetic force, there's a strong force, and then there's a weak force. So which ones of these does the dark matter candidate have to couple to? Gravity. Which ones do we know it doesn't couple to? We know it doesn't couple to the electromagnetic. That's the photons. We know it doesn't couple to the strong force either. It would make stuff. So we would start seeing compounds, like we would see it if it coupled to the strong force, because the strong force, as advertised, is strong. So it would make bonds with stuff. We don't see any bonds in the nuclear structure. So
the strong force, it wouldn't we wouldn't see I guess dark matter stars of some sort.
I mean, if they interacted with the strong force, then we'd see them in nuclear structure. Like we would find particles there because they would get stuck. So we're hoping that they interact with the weak force because that's the only one that's left, and we don't know how to make particles with gravity. We know how to make particles with the weak force. How does that work? I got a neutron. What's a neutron do if I stick it in a jar in my room by itself? It'll decay in about 10 minutes, right? 8 minutes. So what is that? That's a weak process. The weak interaction turns one of those quarks into the other kind of quark and an electron and a neutrino, and those all get spit out. That's the weak force. The weak force can make particles. The electromagnetic force can make particles. What's that particle? Photons, right? The strong force makes particles. It makes quarks and makes gluons and makes all kinds of stuff. So we need to be able to create it in the first place. So it has to coupled to the weak force. Or gravity has to do something we don't understand, which is a certainty, but not an answer for us right now. So, gravity, yes, that's how we know it's there. No for the electromagnetic, yes for the strong force. It would affect nucleosynthesis. We would definitely see that. So we're really hoping that they interact with the weak force. That's what we're banking on in basically all of these, many of these. Not all of them. So we'll talk about machos. We'll talk about axions. We'll talk about neutrinos. We'll talk about WIMPs. We'll say for a minute about curvature and a short minute about hot dark matter. So those are the things that we're gonna go look for. So machos first. This is kind of what everybody wanted it to be. Macho stands for Massive Compact Halo Object, and it was named. So the machos were invented by Kim Greist in reaction to his advisor Joel Premek, who had previously invented WIMPs. So they're machos because of WIMPs. It's hilarious. But they're massive compact halo objects. So 1 kilogram per 100 million cubic kilometers. That's the energy density to close the universe. It's pretty low when you think about it. So a little larger. So it could be just objects. Brown dwarfs, white dwarfs, supermassive black holes that aren't feeding like crazy, mini black holes, medium-sized black holes, all kinds of black holes. Black holes are black, so they're hard to see. Apparently, I really like Longair's section 4.7, if you happen to have a copy of Longair. I don't really draw from that book anymore. Okay, brown dwarfs. Let's talk about brown dwarfs for a second. Do you guys know what a brown dwarf is? So a brown dwarf is kind of this intermediary between Jupiter and stars. So as I pile up hydrogen, at first I just get nothing. And then I get something that's the size of Jupiter. And then if I keep adding hydrogen to Jupiter, what's it going to start doing? It'll slowly get to lithium burning. So as that mass goes up, it'll start burning lithium, and as it starts burning up, as the mass goes up a little bit more, it'll start burning hydrogen or deuterium. And I think that's like 30 Jupiter masses. Maybe it's 15 Jupiter masses. So it's a couples of Jupiter masses. When you get up to like 100 Jupiter masses, you might be burning hydrogen. So that might be a star. The cutoff between a Jupiter and a star is kind of vague because there's not like a phase change, except for burning hydrogen. So brown dwarfs are too small to burn hydrogen. But other than that, they're stars. I mean, they look like a black body. They've got an atmosphere. They're producing their own light. They're really hard to detect, and most of them are named for Kevin Luhman, who's really good for naming them. Lumen 16... I was just going to leave it that way. Lumen 16 is the third closest star to us that was just discovered last year. In 2013, so it was okay. So 10 years ago now, but it was really fun and novel when it was pretty recent because it was that's the third closest object to us, and we just found it because they're hard to find. Brown dwarfs are really dim because they're not very hot. So you would need twice as many brown dwarfs as all of the rest of the stars combined to make up the dark matter. Yeah.
All the stars combined within what? Like the whole universe?
Density. So in the so if you take, say, the galaxy, we know what the dark matter density of the galaxy is. It's about a GeV per cubic centimeter. So it's like a proton per cubic centimeter. It's not very high. So we know what that mass density is. So we know what the total mass of dark matter is. So we would have to have twice as many brown dwarfs in the galaxy as we have stars to make up for everything. Because brown dwarfs don't have very much mass. Not those guys. Not brown dwarfs. Supermassive black holes. The ones that we know about are only a tiny little fraction of their host galaxies. So this is like 0.1% of the whole galaxy mass. I mean, now that's a pretty large fraction, but it's not enough to make up for the dark matter, because the dark matter, we need like 3 or 10 times as much luminous matter as dark matter. So supermassive black holes can't do that. Um, what about black holes that are other black holes that are just in the galaxy? We know there are plenty of those. So what about those? So lensing surveys are really how we closed this. So I have not covered lensing much in this course, just because I can only cover so many things. So when I have a massive object, it bends the space around it so that everything goes towards it. So if I have a star, that's a pretty massive object, or if I have a black hole, or even a planet. So an Earth-sized planet, if it goes in front of a star, you'll be able to see it. So if it goes real close in front of the star, like is in orbit in front of the star, then it'll block out part of the light, and you can see it. If it's further away and goes in front, then it'll lens, and that star will take some of that light that would be going past over my head and hooks it back towards me. So that lens, so that planet or that black hole or that brown dwarf or kind of anything moves in front of a star, and that star gets a little bit brighter. Makes sense? Because of the lensing. So this micro lensing has been really useful. It looks kind of like this. So here is my my dark object, and here's a star. So as the star moves this way, okay, the dark object's probably going, maybe they're going this way, whatever. Fix the object, move the star, and you'll see that the lensing starts to make a ghost image and then makes a ring as they get perfectly lined up. And that ring is bigger and brighter than the original star. So there was a lensing survey. There are several, and there I think are continuing microlensing surveys. But this lensing surveys in the mid-90s looked at the bulge of the Milky Way and the Large Magellanic Cloud for microlensing events. And they found like 100 events. That's cool, that's pretty rare, right? But not enough. So you go say, hey, how rare is this process? I've got this many stars, I've got this many objects, so I expect to see this many lensing events if the dark matter is stars of this certain mass. So there were more than expected, but only 20% of the dark matter halo, and that doesn't help with the Big Bang nucleosynthesis. So even if 20% of the dark matter in the galaxy are machos, that's still not enough for the rest of the galaxy or any of the indicators for dark matter that require there not to be protons. So we've looked. It's not brown dwarfs. Let's see. Is this really what I want this? I guess. So as we discussed before, the D to H gives a baryon density. So remember, omega baryon is the baryon density, so the density of protons in units of the closure density, and that only gives us 2%, which is smaller than the 30% that we need to be consistent with the universe, how the universe looks. This graph really tells us that. So this plot was made by the advisor of the guy who's showing up tomorrow to possibly interview for a job here. It doesn't do anybody any good. So this plot was made by David Teitler, who's in San Diego. What does it tell us? It tells us the theoretical curves of helium-4 mass at the top versus proton density, and then deuterium, and then helium, and then lithium, all as functions of baryon density as the nuclear processes are going on. So we've got protons and neutrons and helium and deuterium, and they're all smashing into each other. Sometimes they break apart and sometimes they form each other. That process is density dependent. So if the density goes up, the helium-4 mass fraction goes up and the deuterium fraction goes down. That's the important bit. That's the knob, is as you make it denser, you get more helium-4 and less deuterium, because you smack the deuteriums together. um, to make the helium-4. This shows that it can't be protons. Um, additionally, so this is the baryon acoustic oscillation bump. So this quantity C, actually, I should write this down. Let me do that. No, come back. Do what I want you to do. Why are you doing that? Stop trying to be clever and do what I tell you to do. Okay, it's there. You can read it, whatever. Giving up. Okay, so this is kind of a weird thing. So this is the average of the density times the density at another point. So I take my universe, I shift it by a point, and I average over the whole universe. And that tells me that if I've got a galaxy here, the probability of finding a galaxy by however much I shifted my universe is delta x. So I average over x, and delta x is how far away I'm looking. And what we see is that there's a bump at about 100 co-moving megaparsecs. Co-moving separation is an H inverse megaparsecs, so that's the co-moving volume. The H is for this Hubble parameter knob. So we get this extra bump. Why do we get this bump? Because in the early universe, as things are streaming away, the protons get pushed out of blobs of stuff, but the dark matter doesn't. So what this tells us is that we get these rings of protons around nuggets of dark matter that make clusters of galaxies that are about 100 megaparsecs across. Because there's a difference between how the protons move through space and how the dark matter moves through space. The dark matter doesn't get pushed around by the photons as much. The baryons only get pushed around by the photons before recombination. So before the CMB, you get these bubbles that you can blow, and then those turn into big clumps of galaxies. It's a kind of cool process, but it shows that the dark matter is not protons. Okay, electron volts. This is just for scale because we like electron volts for everything else. So a proton is about a GeV per C. C is 1, so an electron is 500,000 electron volts. So we're going to talk about axions that are a fraction of an electron volt. Okay, so an axion is a really low mass, really weakly interacting particle, and they're bosons. And they come from some strange strange high energy physics problems that I'm not going to try to get into because I don't understand them well enough to even half-ass an explanation. It comes from matter and antimatter asymmetry. So it's one of these things that we can invoke to understand matter antimatter asymmetry. Particle physics, some particle physicists think that there might be quite a lot of them. They're also really low mass. So, okay, being low mass, so I'm going to tell you that the neutrinos are not the dark matter candidate. Does everybody remember why the neutrinos are not the dark matter candidate? There's a buttload of them, and they have mass.
Because they move too fast?
Because they move too fast. Now, what does that do to what?
Or smaller galaxies.
Right. So smaller galaxies don't form. So if I'm looking at the mass distribution, I get fewer small galaxies if I got a hot dark matter. So I can't form any of the small galaxies. These guys are a little different. So the neutrinos are decoupled from the flow relatively late, and they're relativistic as hell. Axions are produced by not thermal processes, so they're produced by some weird high energy process. Um, so they don't have the same problem that the neutrinos have, in that they just leave because they're all low energy too. So they're cold. Um, um, neutrinos. Okay, so the huge numbers. So the neutrino mass is maybe a couple electron volts, which is really low, but it's there. Um, so it could be enough to close the universe. Although I learned that the neutrino mass actually is maybe a very different mass than the electron mass, because in the standard model, the electrons have mass because they couple to the Higgs field. All of the things in the standard model have mass because they couple to the Higgs field, and the Higgs field slows everything down. Remember talking about dynamical friction? How I've got an object that moves this way and it focuses all of the stars behind it and then they slow it down? The Higgs mechanism is similar. So when you've got an object and it's moving, it's going to attract more of that Higgs field behind it, which tends to slow it down, which is why things don't move at the speed of light. That's what it means to have mass, is you're not moving at the speed of light. So anyway, so electron mass, so neutrinos have mass, but we don't really understand it like all the way we don't understand the neutrino mass. It could be maybe a couple percent of the dark matter mass, but it's not the dark matter because, as we just said, they would destroy all the small galaxies. We have little galaxies that have dark matter in them. I think I did that. WIMPs are weakly interacting massive particles, and so these are objects that are like 100 GeV, so these are like 100 protons. Big objects. The standard model doesn't have any objects this big, but you can extend the standard model by making Bizarro Universe standard model, where you turn all the leptons into bosons, and you change the charge of everything, and I can't remember what else. There's a couple other things. You just write down the standard model, and then you change a sign in a couple of places, and you get these huge, massive objects. That also works kind of like a standard model. So there could be this whole other standard model of particles that are just way bigger that exist in the universe. So they probably make stuff too, right? I don't know. So one of these could be it. So they get names like the sterile neutrino and the lightest Kaluza-Klein particle and the lightest supersymmetric particle. So supersymmetry is this bizarro universe. The littlest one of those might be it. The biggest one of those might be it, but has never been discovered. I don't know if it really exists, but it's something that the theorists have been talking about for a long time. So WIMPs come out of this this supersymmetry. Let's bold that up. Metric perturbations is something that other books go through, but I'm not going to get into. This is basically curvature. So curvature has energy. So maybe there's wiggles in the curvature in space, and that gives us dark matter. Math says yes, but GR doesn't say yes. Do I want to go into this? Yeah, okay. So this is the power spectrum. So this is big stuff on the left and little stuff on the right. So this is wave number in the horizontal axis, which is 1 over wavelength. So little stuff over here and big stuff over here. These curves describe the power spectrum of galaxies for cold dark matter and hot dark matter and some other nonsense. And you can see the hot dark matter curve tanks. It doesn't make any of the little stuff, whereas the cold dark matter can make all the little stuff. Okay, so machos, totally ruled out. Axions, not ruled out. WIMPs, not ruled out. Curvature perturbations, pretty well ruled out. So we're going to talk about a couple things. We're going to talk about direct detection. So this is, I have an object that ought to light up when a dark matter hits it. and we'll look for WIMPs and axions. There's indirect detection, where I look for a signature of something else. Dark matter particles annihilating and giving me something else. Or you can make them in a lab. So there's this cool graph. So I have let's not put arrows yet. So I have this cartoon of two dark matter particles and two standard model particles, and I can think about this cartoon in lots of directions. I can make time move in this direction, and then I start off with a dark matter particle and a standard particle. The dark matter particle bounces off, and the standard particle goes this way. So they recoil. They exchange a whatever, W or a Z boson, and they bounce off each other. So this is direct detection. I could have two dark matter particles that annihilate and give me two standard model particles. So actually, this has got to be X and X bar. Because if I make a particle, I don't make another one of it. I make its antiparticle, but that's fine. So I can have two dark matter particles, and they annihilate. This is indirect detection, so I'm going to point my telescope at a spot where I think there might be a bunch of dark matter and see something. And I'll show you that there's a couple of spots where they've pointed their telescopes there and they see something. So maybe there's some indirect detection. There's one measurement that says there's direct detection. Or I can take two standard model particles and smash them into each other and get two dark matter particles. And this is direct. This is production. So these are the ways that we can find the dark matter, either by seeing it in the lab, seeing it in outer space, or making it in the lab. So let's talk about each one of these real quick. So here are three, and actually this slide's kind of out of date now because that's what happens as a running theme with my slides. It's a running theme with astrophysics. So what they do, so there's one called ADMX that's in Washington, and one called PVLAS, which I think is in, I think it's in Europe, and Karak, which is in Japan. They do a couple of different things, but they're all about, a lot of these are about, let's save that cartoon, because that's a good cartoon. So the way these axion searches tend to work is you have some bottle of stuff that you think is going to make axions. And I think there has to be a large magnetic field. So there's like an 8 Tesla magnetic field. And you shine a laser through your stuff and your magnetic field, and we think we'll make axions here. And then you have a wall. And you put a detector on the other, the detector looks like a grad student here. But, so you put a detector on the other side of the wall. You shouldn't see anything from your laser, but if I can make a couple axions, and the axions can go through the wall and then turn back into a photon, then I can see them. There's been a bunch of particles that we found this way. where you have a wall and something that shouldn't go through the wall does. But they haven't seen anything. So they're putting limits on the masses. So this ADMX has excluded masses between 1.9 and 3.3 micro electron volts. That's a very small mass. I was talking about giga electron volts on the other side. So there's a huge range of masses that we have to look in for what the dark matter is. So the Axion searches are cool. They're ongoing. The WIMP searches, when I started writing this talk, the WIMP searches were where a lot of the energy was going. So we'll look for WIMPs and axions in these methods as well. But so we'll talk about direct detection, indirect detection, and collider production of WIMPs. So here is us. Here is the sun moving around the Earth. Nope. The Earth moving around the sun, and the whole system moving around the galaxy, right? So so we're traveling in that direction. Sometimes we're going this way. Sometimes we're going this way. Sometimes we're going that way. Sometimes we're going that way. So I take my telescope, which is just a tank of maybe water, maybe xenon. We'll talk about that. And if I can see some signal that modulates with where we are in the solar system orbit, then that's a big signal. And we know how much dark matter density there should be. It should be in the Milky Way at the solar circle about 0.3 gig electron volts per cubic centimeter. So this is how much dark matter we know it has to be there. So now the question is, how many dark matter particles am I going to get? I know that the density of dark matter particles times the mass of the dark matter particle has got to be 0.3 GeV per centimeter cubed. So if the mass is really little, then the number is really large, and conversely, if the mass is really large, then the number is really little. So this puts brackets on how sensitive my detector is, because if the dark matter mass is very large, then I'm never going to see one. If the dark matter mass is very small, then I'm never going to see those billions of things that are streaming through my telescope. So the two important parameters are the cross section, which is how big the particle is. Big is kind of a funny idea because these are quantum mechanical objects. There's not an edge. There's just a probability that you're going to run into it. So the cross section is the probability that you're going to run into it based on the object. And the mass is its mass. So the lower end of the mass is set by the detector sensitivity. So lower dark matter mass gives me lower particle recoil velocity. I'll show you what that means in a second. Basically, I've got a tank of stuff, and in my stuff I've got nuclei. And those nuclei are made of nucleons. And when I have a dark matter particle, it'll smack off one of my nuclei, and if the dark matter particle isn't very large, it's not going to move the xenon nucleus very much. So there's a low mass detected. There's a high mass because the flux decreases. So in general, the expected rate is about an event per day per kilogram of stuff. So, and that means you have to actually be able to. So that just means how many happen. Then you have to see it, because this is one nucleus in your whole tank of stuff that's doing something weird. So, so there's two. There are two kinds of interactions that you could have. There's a magnetic interaction and an electric interaction. So the magnetic interaction depends on the spin of the particles, and the electric one doesn't. So there's two. So the next couple of plots are broken up into spin independent and spin dependent. The spin dependent ones don't depend on the target mass, only on their nuclear structure, which is handy. You can just get something with a large magnetic moment to power your your business. The other thing that you need to do is suppress the background. So the background are all of the things that are going to light up your camera that aren't the thing that you want. So, so gamma ray photons from the environment will light up your detector, whatever your detector looks like. There's lots of ways you can make a detector. Beta particles from beta decay, so that's a hot electron or a positron that comes out of a neutron. Those are problematic. And then neutrons. Fortunately, these all have some kinds of so neutrons are nice because they will scatter off more than one object. So when I have a bunch of scatterings, I can just take that out if I see an event. I know that was a bare neutron that came through my detector, which is going to rattle around like a dark matter particle because they don't have any charge. So they're just going to smash into stuff. Well, let me show you. I'm going to actually show you the tank. So this is what one of these objects look like. There are 10 or 15 detectors like this. So this is the Xenon 100, and they're now up to the Xenon 110 or 1 ton, which is 10 times larger. So what do? You get a large tank of liquid xenon, and you put it in an electric field, and you put some cameras on it, and I'll show you those in a second. Then you put that whole apparatus way underneath a mountain range. So this is the Gran Sasso lab, which is a mile underneath the Italian Alps. Why do you need to put it underneath the Italian Alps? Well, because what's that? Screen out all the background crap. So the neutrons are easy to screen out, but the muons aren't. Muons come from outer space. They come from the upper atmosphere. Random garbage hits the upper atmosphere and sometimes makes muons, and muons can go clear through a whole lot of stuff. So you put it through. You put your detector in a abandoned mine, way underground. Let's see. I got a movie of it. I'm trying to remember where I put the movie. I hope I put it here. I did. Nice. So here's a zoom in of the detector. And then they cut it away. So what's in here? Let's hit pause for a second. So I have a strong electric field going up. And I have photomultiplier tubes, which are just really sensitive cameras. So a photon comes in and then it does a cascade of extra photons. So you get a bunch of photons, with a little grid of wires and stuff. Doesn't matter. Special camera. Good camera at seeing photons. So a dark matter particle will come in and hit a xenon nucleus and move it. Because I moved a charged object, what do I get? Before? Photons. When you move a charged thing, whenever you accelerate a charge, you get a photon. So I shift the nucleus and it spits off a photon just because it moved. Then some other stuff might happen. That's the thing that we want to see. We want to see a photon. We want to see a blip of light because a nucleus moves, and then nothing else. Other things, if I have, so we have an anode grid and a cathode grid, and then we have cameras on the top and the bottom. The electric field is, I guess, going down in this picture. What's the electric field do? Well, if I have one that's strong enough to spit off an electron, so if I have an electron that hits my nucleus, that's going to spit off an electron that's going to spit off a bunch more electrons because there's this electric field. So the electric field will accelerate that liberated electron, smash it into a bunch more electrons, and give me a whole boatload of electrons. Why do I want that? Because I can tell the difference between that and a dark matter particle, because then I got a whole bunch. And I'm like, okay, that was an electron. So you see the electrons go up and hit the photomultiplier tube, and you see here there's a blip from when the nucleus got hit by the dark matter particle, and then another blip when all those electrons actually drift up towards the photomultiplier tubes. So that's not a signal that you want. That's what an electron looks like. But a dark matter particle, I think the dark matter particle is next, or a neutron, there's just a blip of light, and only maybe a couple of things come out. So a couple of electrons, like maybe you knock off only one electron. But you get one peak, and then not much else. Now a neutron will look similar, but it would do that a couple of times. So if I see a couple of little blips, then I can reject that signal too. So here, they have a couple. Oh yeah, come back. Oh man. So here is the ratio of the heights of the first blip and the second blip, and they have a couple where the second blip is real weak. So maybe that's a detection. We'll see. These guys have not announced a detection yet. So that's Xenon 100, and this is now this plot's now out of date. The new plot, you really can't tell the difference, except for the axis. The numbers are different. Yeah.
Isn't this the same thing like solar neutrinos?
Mm-hmm.
How do we know it's not that?
Solar neutrinos give you a specific Cherenkov pattern. So when the solar neutrino enters the cavity, they're going real fast, and they make a Cherenkov ring, which is like a sonic boom. So when you have an airplane and it goes faster than the speed of sound, you get a sonic boom because the sound all piles up. You get a pile up of sound that's trails behind the object. If I have an object that's moving faster than the speed of light in water, because the speed of light is slower in water because it's got all those electric fields, it'll make a similar sonic boom kind of thing, which is a ring of light that you can detect. And from that ring, the properties of the ring, you can tell where it came from and what kind of neutrino it was and all kinds of cool stuff. So that's a good question. So they'll totally have those events as well. So this was the state of the art when I wrote the slide. The state of the art looks basically the same except slid this way, and there's a couple more experiments. But the story hasn't changed. The story is still, here are our limits of detectability. We have reached them. There's not an object. There are no dark matter particles. So this is Xenon 100, which I think is the most robust and strongest limit, and it has excluded everything above this line. Now there are a couple of things, specifically this Dama measurement, that kind of maybe saw things, but not enough. They can measure axions at this facility too. I'm not sure what else I have to say about that. So the spin-dependent experiments are similarly give us lower limits that are not achieved yet. So let's look at what these limits are. So this WIMP mass, so 100 GeV here. This is a large object. We're probing down to the 10 or 1 GeV. So this curve is a little lower now, but not a ton. So we get down to about a GeV that we can probe, which is pretty small. And the nuclear cross section, these are small. These are in centimeters, centimeters squared. This is like 10 to the minus 41 inverse centimeters squared. That's a really little number. Okay, so indirect detection. Did anybody have any questions on detectors? There's more that I could say that I don't, but I'm gonna stop. So indirect detection is when dark matter, so here C is a dark matter particle, goes to Q, which is a lepton or a W or a Z or something like that. And then those guys decay into photons and protons and muons and stuff that we could see. So we expect dark matter to clump. So we're going to look in neutrinos, gamma rays, and positrons. I'll tell you why in a second. So the annihilation rate comes from the capture rate, because the sun can only annihilate the dark matter that's in it. Why is the dark matter going to be in the sun? Because it's massive, so it should fall in. So we look at massive objects like the sun or Sagittarius star, the black hole, and look for events there. I don't think I care a ton about that. Math. Let's jump to the. Now let's look at these ones too. So this is Super K. Have you guys seen this before? We had a great job candidate. We want to hire a neutrino person. We had a great candidate who came in and told us all about this detector and all the kinds of things. And she said she doesn't have a picture of herself in the boat, but she's been in the boat. So this is a huge tank of water, and these are photomultiplier tubes. Each one of these is a little camera, and they're like, yay big across. And there's, I don't know, like 40,000 of these things. This is an enormous facility. Normally it's filled all the way up with water. They drain it so they can fix the stuff, so they don't have to have divers. So the water is super, super clean, because that way you don't have like banana particles giving you beta decay. So bananas are radioactive, as you know. So Super K, this is another way we can find neutrinos. So this looks for the neutrinos that would come from self-annihilation of dark matter. Another cool telescope is Ice Cube, which is the biggest telescope in the world. It is so this is the ice in Antarctica, and then you have like 3 kilometers of ice and then rock. So they drill holes that are 1 kilometer long through the ice and drop these cameras on the strings. They have these cameras that are round. And there's like 1,000 of them on a string, and they lower the string down to the hole and then let it fill back up with ice. And the cool thing about this camera is it's such a huge volume, but it's also incredibly clear. The mean free path for a photon in this is like 1 kilometer. It's really, really pure ice, because it's just been sitting there getting snowed on for the last 100 million years, right? So this is a huge detector volume. Why do we need a huge detector volume? Because we need to be able to detect the thing. So we need to detect the photons. So the more interactions that you have, the more likely you'll see stuff. The larger the actual volume you have, the more likely you'll see stuff. So we have a huge ton of ice. So the Eiffel Tower and Ice Cube are here for perspective. So far it has not yet been a good day. They have not seen any things. They have seen some really crazy high energy particles. Like they've seen some really ridiculous particles with Ice Cube.
There's one where like Big Bird, like where they have like it looks like a bunch of like green and red dots, and it's like the redder it is and the bigger it is, the more higher energy it is. I think I've seen one of those like those pictures.
Yeah,
I
probably.
think one of them they named Big Bird, and it's just like massive energy spot. Like it's like,
Yeah, they have cosmic rays that have the momentum of a baseball that's been hit at a home run baseball. So which goes like how fast does a pop fly go? Like 150 miles an hour. There's a proton which has basically zero mass, is going so fast that it has the same momentum as a baseball. It's a very cool telescope, but they have not seen anything yet. There's one. Fermi. So Fermi is a gamma ray telescope in outer space. Gamma ray telescopes on the ground don't work because gamma rays don't go very far, but in outer space they work great. And they see this spot, and again, I need to go update my slides because I don't know how robust this is still, but I bet it's still there. They see this spot of excess gamma rays coming from the galactic center. excess relative to what? I've said several times that we really don't understand black holes very well. So you really have to understand the systematics of the system to be able to say, I have too many gamma rays coming off of this object here. Well, how many gamma rays were you supposed to get? If the answer is 0, then that's easy to measure. But if it's a violent place like the center of the universe, like the center of the galaxy, there's a lot of neutron stars and pulsars and things that are spitting off gamma rays as well. So you have to understand all of those systematics. So this is a very difficult measurement to make because you have to say, here's a bunch of noise. I understand most of the noise, and the noise that's left is a real signal. So this is ongoing. I haven't needed to change this slide because there has not been a press release that I have actually believed that said we have a confirmed signal. I would have fixed that. This is still work in progress. Positron. So there's this Russian spy satellite, and they let us put a detector called Pamela on the backside of it. There's another one on AMS-2, which is on the International Space Station. So this is the count of positrons. So positrons, again, don't live very long. They run into an electron and they die, right? So positrons are pretty rare and created by violent processes. So something serious had to happen for you to get a positron with any kind of actual flux. So this graph shows the total count of positrons here, and then the background from nearby pulsars and stuff is here. And you can see there's a little bit of an excess, maybe over what we expect for the pulsars. Maybe there's a signal there. This one I hear about from time to time, and still hasn't seen anything robust. And then the last way you can look for dark matter particles is with collider searches. So one of the ways this works, the common way this works, is they look for a missing momentum. So I have my collider, which looks like a barrel. I have a stream of protons, or protons in red. Going that way. Stream of protons coming this way. What is the rest frame momentum of, actually, what is the lab frame momentum of the collision of two protons in the middle of my collider? So this is some kind of detector. So what's the relative momentum of my two objects? Well, it's large along Z and 0 along the other two axes. Right? So what usually happens if I look at the end, here's the hole, I'll have events happen in the center of my detector, and then I have my detector volume here. However this works, there's lots of different ways that detectors work. Sometimes they're pieces of plastic that glow when particles hit them. Sometimes they're strips of electric wire. Sometimes they're clouds of gas that get lit up. There's lots of different ways that you can put a particle detector out here. But if I see a particle go out this way and a particle go out this way, why do I know that there's something wrong with this? If I have an event and I measure a particle, and I measure this particle and I measure this particle.
Something has to be there.
Yeah, something has to come out this way too to balance the momentum. Right, so there's this missing transverse momentum. Missing PT. Missing momentum problem, where you say, okay, I saw these two things, I didn't see something else, so I have no missing momentum. This is one of the common ways that people are looking for these, if you're just missing some stuff that you didn't measure. There are a couple ways that this can happen, but you can, in principle, you can tell if it's dark matter. So to date, we have not found any of those either. The high luminosity run of the Large Hadron Collider is going to turn on in a year or so, and maybe they'll see it, but we haven't seen it yet. So, I don't know. Okay, so I think that's the end of my slide deck. Does anybody have any questions on any of these things that I've gone through? Okay, so we talked about machos, which are massive but conventional objects. We look for those and we don't see them. Talked about neutrinos. Can't be neutrinos, they're too hot. They kill all the little galaxies. Maybe it's axions, which are relationships between photons and magnetic fields, and they're really little particles. Or maybe it's WIMPs, which are really big particles. And each of these, we can find the axions and the WIMPs in one of a few ways. We can see them with direct detection, indirect detection, collider searches. Let's see. I got 12 minutes left, and I've run out of things to say. Probably.
Is it possible for dark matter to just be an amalgamation of multiple things we haven't ruled out yet?
Yeah, there might be more than one dark matter, and that comes up a lot. So often, there could be a whole dark universe. They call it the dark sector. There could be a whole dark everything. If this supersymmetry is right, then there's a whole family of particles, and they could be doing stuff that we don't know about. There could be a whole universe that exists right here. I am skeptical. So it's possible that it's a combination of these. Oh, the other thing, I haven't talked to you guys about MOND yet, have I? That's all right. So there's one other thing that I want to say. I'm out of power. One other thing I'm going to say, and that's, so everything that I've said today assumes that the theory is right. It assumes that general relativity is correct. That's really the big assumption. Because if general relativity is wrong, then we have problems. So there is a theoretical idea called there are a number of theoretical ideas to try to fix dark matter without making it a particle. The only one that really has much teeth is called MOND. For modified Newtonian dynamics. And what it says is that hang on one second. This is one of those things that normally I just know off the top of my head, but I'm going to ask the internet real quick because I'm forgetting. Now I got no internet. Oh man. Okay, slight inaccuracy. So this is the force law for gravity, right? So what MOND says, and okay, take this with a grain of salt because I might have this in the wrong spot. So what MOND says is we just add this A down here to tweak the acceleration so that when the acceleration gets really small, it tends to a constant value. Yeah, that's all I was going to say. So So the thing is that when the accelerations get small, force goes to a constant. Which doesn't make a lot of sense like from a theory point of view, but it makes sense for flat rotation curves. This is really about matching flat rotation curves. And it works okay for, it actually works great for spiral galaxy dark matter because it was designed to work for spiral galaxy dark matter. It doesn't work for anything else. There are papers where they try to kludge it together, but it's the kludge. So it could be, and that's the one thing that's missing from this slide, is it could be something else that we haven't discovered, or it could be that the math is wrong. At this point, my professional opinion is it's going to be something that's really, really weird. Kind of like we didn't know how photons propagated, so they had to invent relativity where the speed of light is constant for all observers, which is a really bizarre thing to get your head around. But that's how nature works. So my suspicion is that dark matter is going to be something that's just super bizarre. No, weirder than that. I can get my head around this.
Yeah.
It's going to be something that I can't get my head around, which is the hard part. That means I'm not going to be able to find it. So I think it's, I don't know, that's my suspicion now, but we'll see. People keep looking. Any other questions? Everybody good?